So our next speaker is Sage Wire, who's talking about Ceph, which he designed as part of his PhD and has continued to work on for managing distributed storage systems at scale. Sage.
Thank you. So today I'm going to talk about a couple things. I'm going to talk a little bit about, just a little bit of background, what the current storage reality looks like for the administrator who's faced with the task of storing petabytes and exabytes of data. I'm going to talk a little bit about Ceph and what it does because I can't help myself. And then at the end I'm going to talk about how we try to make Ceph easy to manage and deploy in large environments. So I guess the high-level question you guys should be asking yourselves is, why should I care about another storage system? And there are a few things. So first of all, there's sort of the old reality of what the storage administrator used to be faced with. So you used to have, a small number of hosts. You'd probably have some direct attached storage, something like that. As your enterprise scaled, you'd probably buy some network attached storage. The NetApps that came out in the 90s, those were pretty awesome. You use NFS and Cephs, stuff like that. If you're a larger enterprise, maybe you are lucky enough to afford a SAN, which was pretty cool. These types of systems have scalable capacity and performance up until a certain point at least. But the problem is that they have poor scaling of either the management or the price. Either you have to buy 100 of them and you cost 100 times as much and you have to manage 100 times as many systems, or they cost an order of magnitude more and you get all this fancy unified management and so forth. So not scalable for things like the cloud. The new user demands are a little bit different for you as the administrator. So you have this whole thing called cloud that you might have heard about, that your IT manager might be harassing you about. Usually this means you have lots of disk volumes, you need sort of automated provisioning, you have much larger data sets, things like objects and logs and images and so forth. There's also this thing called big data that you may or may not have some idea what that actually means. There are sort of many different definitions, I suppose, but usually it means something to do with distributed processing and very large data sets, unstructured data, that sort of thing. But you also have the continued growth of all your existing storage. You still have files and directories and home directories and iSCSI volumes and so forth that you still need to deal with. So suddenly the storage administrator has a lot on his plate and needs to sort of figure out how to deal with all these types of different use cases. So that means that there are sort of expanding requirements, lots of different types of storage that you need. So there's object storage maybe for lots of images and video files. There are block devices that you need for your legacy stuff that used to be consuming your SAN. Maybe you have all these virtual machines that need block devices. You still need a shared file system for some things. And then there's this unstructured data and you frankly probably don't know where it belongs. There's also, of course, the problem that you suddenly have these increasing demands on scale. You just have to store petabytes and petabytes of data instead of maybe terabytes. And that can be problematic. So there's also, you want to be able to deploy this on heterogeneous hardware because you start small and you grow bigger. Maybe you can't buy the same boxes. And things like reliability and fault tolerance become increasingly important in these types of systems. You also have, of course, cost pressures. So you want your system as it scales out to be ideally a near linear function of price, size and performance. So if you're twice as big, you're spending twice as much money and not 4 times as much money, so you can actually make a real business about it. You need incremental expansion as your system grows out. You don't want to have to replace your old system with a new system. You don't want to have vendor lock-in. If you made a horrible decision on your first petabyte, you don't want to be locked into that decision on your second petabyte. You want to be able to hopefully learn from your mistakes. And all of these things are sort of pointing you in the direction of having an open solution, both in terms of being able to choose your hardware and be able to choose your software. Also, your time is precious. I'm sure you all agree with that. So things like ease of administration and ease of automation, so you can hopefully replace yourself with a very small bash script. You don't want to have to deal with anything like manual data migration between all these different servers that you're deploying. That would be horrific. You want painless scaling so that you can expand your cluster as your capacity increases, and you can also contract your cluster as your old kit becomes useless and all your drives are failing. You can tear it out of the system. In short, you want something that's sort of DevOps friendly. You can automate it, you can integrate it, and you can sort of easily and efficiently deploy these huge data centers with hopefully a very small staff. So this is where I sort of make a diversion and talk a little bit about Ceph because that's what I like and that's what I know about. So Ceph is a distributed storage system. It's designed from the ground up to be large scale, so tens to thousands of servers, tens of thousands, terabytes to exabytes. It's designed from the beginning to be fault tolerant, so there's no single point of failure in the system. It's also designed to run on commodity hardware, so systems at scale are going to have unreliable components, so that you want the reliability of the overall system to be much higher than the reliability of any individual component. And as a result, or of necessity, you want these systems to be largely self-managing and self-healing so that they're not labor-intensive to actually manage and run. So Ceph is a unified storage system because it offers a variety of different interfaces with which you can access your data. So there are object APIs, either sort of our low-level native object protocol that takes full advantage of all the bells and whistles in our low-level infrastructure. There's also a higher-level object API that's compatible with Amazon S3 and Swift for things like RESTful access and storing images and so forth. There's a block layer that stripes virtual disks across objects and has cool things like thin provisioning, snapshots, cloning, stuff like that. And then on top of all this, there is a distributed file system that has, massive scalability, strong consistency, snapshots, recursive accounting, and some other fun things. So the real question then is, taking a step back, is how do you design a system that is designed to scale, both in terms of the overall capacity of the system and your ability to actually manage it and deploy it. So at a very high level, you have some human, or maybe some human application cyborg or something that wants to talk to some data that's stored on some disks. And because we're computer scientists, we put a computer in the middle. So that seems like a good idea. In reality, you have multiple human cyborg people who are trying to access your data. In reality, the situation looks something more like this because you have lots and lots of people and your data is so important. This obviously does not scale. What you really need is a situation where the people who are accessing the data can talk directly to the storage servers that are storing the data. So you need this sort of scale-out architecture. So Ceph does this by beginning with a distributed object store that we call Rados. Rados is the layer that will take bajillions of objects distributed across tens, hundreds, tens of thousands of servers and make sure they're replicated across multiple servers. They're well distributed. It deals with things like hardware failure and data rebalancing and so forth in a fully consistent, fully sort of self-healing, self-managing way. And then on top of that low-level distributed object store, we build all kinds of fun ways to access your data. So the simplest is librados. This is sort of the low-level library that lets you get complete access to that distributed object store. If you're building, the next Flickr or some Web 2.0 application, this is sort of the thing that you'd be looking for. On top of librados, we have something called the Rados Gateway. This gives you a higher level RESTful object API. So if you want something that's compatible with S3 or OpenStack Swift, then this is your ticket. There's also something that we call the Rados block device that gives you a virtual disk abstraction. So imagine a virtual disk that's striped across lots of objects. Those objects are then stored in this highly available, redundant distributed object store. And then finally, the sort of exciting piece is there's also a fully distributed file system with scalable metadata and snapshots and native Linux kernel support and all that good stuff that also leverages this object storage substrate in order to provide all the storage service. So lots of different ways that you can sort of consume this storage available. But the core to all of this is this red component at the bottom. That's Rados. So the question is, why do we start with an object store? Why don't we talk about blocks or files or something like that? And there are a couple of different reasons. The first reason is that blocks are a terrible interface for building a distributed system. So objects are much more useful than blocks. They're easier to use. You can name your object whatever you want. The object can be any size. And you can build sort of a relatively simple API and also sort of cram all these rich semantics into it in a very sort of natural, easy to consume way to build higher level services on top of it. On the flip side, objects are much easier to distribute than files. So files have this whole file directory hierarchy that's very complicated and doesn't naturally lend itself to distributing across tens, hundreds, thousands of different servers. File systems also have all these weird POSIX semantics that can update multiple objects at the same time, whereas a pure object API means that you're talking to a single object and it's very simple and easy to distribute across lots of different servers. So Ceph starts by building a distributed object layer and then builds all this, everything else on top of that. So a very simple picture of what that looks like. You have a system, you have lots of disks. They might be hard drives, they might be SSDs, they might be Fusion IO, they might be, I don't know, what else, carrier pigeons, something simple. On top of those disks, we use a local file system. So these disks are exposing a block device to the kernel. Again, we sort of hate blocks. We hate dealing with the details of block allocation and so forth. So file systems have already solved this problem a million times, so we use something like Btrfs or XFS or X4 to sort of manage the local storage on an individual node. And that gives us sort of something that's a little bit easier to consume. And then on top of that, we put the Ceph object storage daemon. This is the part that's responsible for managing the local storage on that node and presenting it to the user and to the rest of the cluster and making sure it's replicated and available for reads and writes. Typically, then you have a whole bunch of these things. You stick them in a single box, and then you have lots of these boxes that you fill your data center with, and that comprises your cluster. So mostly your cluster consists of these object storage daemons, lots and lots of them. Again, you can put it on any type of hard drive where you want. And they're the ones for actually serving objects. We push as much intelligence into those nodes as possible so they can actually do useful work when you're not sort of watching them. But then there's a small number of nodes that we call monitors that sort of are responsible for herding the cats to make sure that everyone has a consistent view of who's up and who's down and what everyone's supposed to be doing. So usually 3 or 5 of these in a typical cluster. And then from the human cyborg's perspective, who's utilizing the storage cluster, they can sort of ignore all the details of all these different nodes, and they are sort of treating the storage cluster as a single logical pool of objects. They don't sort of want to deal with all these details. And then the cluster itself is sort of self-organizing. So one of the key challenges in building these systems, and so that you don't have to deal with, where does my data go, is how does the system decide where to store your data? So the basic requirements are that we want to have all of our objects replicated multiple times. And we want them to be automatically placed in the cluster and migrated and so forth when the cluster state changes over time. And one of the sort of ancillary requirements of that, because we're dealing with data storage and data is important, is that we need to pay attention to the physical infrastructure that you're storing in. So typically you have disks and hosts and racks that are connected by switches and power supplies. Then you have lots of racks in your data center. So you might want to make sure your replicas are separated across racks so that if you lose a power circuit or a top of rack switch, you don't compromise availability. But you might want to constrain all your replicas to the same row maybe so that you don't increase the load on your network, something like that. So there are a couple of different ways that you can sort of achieve these high-level goals. So the most trivial is that you as the user choose a node to store your data on and you put it there, and then you have to remember where it goes. That's sort of a non-starter because the cluster might change over time. You come back a week later, maybe that node that you stored on doesn't even exist anymore because it went up in flames. A more typical approach would be that the system is responsible for remembering where all the objects are stored. That works okay, except that as the system scales, just simply keeping an index of where everything is stored in the cluster becomes a scalability problem in and of itself. It also means that in order to find your data, you have to sort of do a lookup to figure out where it is and then actually go find your data, and that can be undesirable. And so modern systems, modern architectures use something called, use hash-based placement algorithms so that you can calculate the location in the cluster sort of as a function of the name of the object and the state of the cluster, which is sort of difficult for some people to wrap their head around, but is sort of the magic that makes these systems really work. So Ceph uses an algorithm called Crush that has sort of a few key properties. One is that you calculate the location of your data. You never look it up. So you just spend a few microseconds doing that, and then you get the answer, and you talk directly to the server that has your data. It provides a stable mapping. So you might have 1,000 servers. If a small number of those go down, a small amount of data will have to migrate and be re-replicated across, but most of the data will stay put. That's important when disks have lots of data, but they're actually pretty slow at copying it around. But one of the most important things about Crush is that you can specify how your data is distributed using sort of high-level rules. So you might say, I want 3 replicas. I want them all in the same row of the data center, but I want them in separate racks. Or maybe I want 2 replicas. I want 1 in this data center and 1 in that data center, that sort of thing. And Crush will sort of obey all of these sort of constraints, yet still give you this ability to calculate the location and have data sort of magically work without having to store it. So what this looks like in practice is that you have a bazillion objects. They're actually sort of binned up internally into these things called placement groups that we make look like a rainbow, and then we use Crush to decide where those placement groups get stored. You actually have lots of these, so they get sort of randomly distributed across the cluster. Everything's replicated multiple times. Your storage nodes are evenly utilized, that sort of thing. And then the client, when it needs to find some data, it'll have sort of a picture of what the cluster state is. It'll calculate the location of the object. It'll talk directly to the storage nodes, node or nodes that I need to in order to read your data. But most importantly, from sort of a scalable distributed storage management perspective, when a node fails, the monitors that are sort of keeping track of what's going on here, all they have to do is sort of tell everyone in the cluster that this node is now down. And then the other copies of the data will sort of efficiently and magically realize that their data needs to be replicated or migrated somewhere else. And in a fully distributed and sort of peer-to-peer, uncoordinated fashion, they will make sure that data gets copied to a new location and your overall durability is restored without any sort of central coordination that's actually telling you what to do. So at a very high level, Ceph is essentially pushing a lot of intelligence to the edges of the network, sort of to the storage nodes, so that they can perform all these sort of menial tasks that administrators used to have to do with very little central coordination, so you have very good scaling. And then the client comes back later, it has sort of a new view of what the cluster state is, and it can find the data in a new location. So sort of stepping back again to sort of look at what Ceph can provide you. So again, you have a number of different ways you can access your data. If you're using sort of the low-level Librados APIs, then you can build your Web 2.0 application, link directly to Librados, and sort of directly access this huge pool of storage. So if you're dumping images or something into the system, this is your ticket. It's very scalable and efficient and lightweight. Bindings in all kinds of different languages. You can do things like embed computation into the storage nodes and do transactions and atomic compare and swap and all kinds of fun stuff. Rados Gateway is more useful if you're sort of providing a web-based service where you want S3 and Swift compatibility. So you have sort of the scale-out array of web servers that are speaking HTTP RESTful protocols out the front, and then on the back end, they're talking to the storage cluster. RESTful on the front, native on the back end.
Sorry, can you keep talking to the front because we can't hear you when you're...
Oh, sorry. No problem. Yeah, there we go. My laptop screen doesn't mirror the display because the Samsung video drivers are annoying. That doesn't work. Sorry about that. Is that better? All right. Figure this out. That comes later, after the beer. So then there's the Rados block device. So if you're deploying a cloud, lots of virtual machines, they need virtual disks. So essentially you have a virtual disk that's striped across objects that's being presented to your virtualization container, maybe KVM, which is then presented to the VM. Because it's shared storage, you can do some cute things like do live migration, moving the virtual machine between hosts, which is kind of fun. It's good, makes for a good demo. There's also an in-kernel client, so you can map like a standard block device, dev RBD1, that actually is backed by your Ceph cluster. So that's also fun. Rados block device has all kinds of bells and whistles. You can do snapshots on images. You can do copy and write clones of images. So if you have a static operating system image, you can clone it for every VM in an efficient way. And there's native support in KVM and the Linux kernel. It's well integrated with OpenStack and CloudStack. Things like Zen are coming soon. There are prototypes for that. And from a sort of a management perspective, the idea here is that you don't want to have to sort of manually specify that this particular VM has this iSCSI volume over on that server, and then make sure that that gets migrated when that server fills up, that sort of thing. These RBD volumes are striped across the entire cluster. The cluster's capacity is sort of elastic. You just deploy more storage when you need it. And so it makes it very easy to manage the infrastructure there. And finally, the Ceph file system. So typically when people have large file deployments, they just end up deploying lots and lots of different filers, and then they map, different sets of home directories to different servers. It's a huge pain in the butt. Ceph, in contrast, looks at it a little bit differently. So the idea here is that you talk to a smaller set of metadata servers that are responsible just for the files and directories, and the I/O goes to the OSDs, the storage nodes. Again, so that's sort of elastic. And then these metadata servers are sort of responsible for taking this sort of non-trivial problem of taking a complicated directory structure and distributing it across however many metadata servers you've deployed. And so what they'll do is observe the workload and sort of automatically and dynamically decide that this subtree is about 50% of the traffic, so I'm going to hand it off over to that guy. And they'll do this sort of adaptively over time using their internal temperature tracking stuff, and they'll automatically make sure that you're utilizing all the available metadata server resources to distribute your workload so that your administrator doesn't have to go find a home directory to move to another server so that you don't fill up your cluster. It has a couple other cute features that are fun to point out. So one is that the metadata server tracks the recursive statistics for the file hierarchy sort of in near real time. So when you do an ls-al, the size for a directory is actually the total amount of data stored in that subtree of the hierarchy, which is kind of cool. You never have to do a DU again. This is sort of near real time and very efficient. It lags by a minute or two, so it's not perfect, but that's the price you get for actually making it go fast. You can also do things like snapshot arbitrary directories in the file system. So there's this hidden .snap directory that's sort of similar to what you get with NetApp. To create a snapshot, you just do a make dir. It includes everything sort of nested beneath it in hierarchy. You have the usual snapshot semantics where you delete a file and you traverse into the snapshot, it's still there, that sort of thing. And then when you're done with it, you just do an arm dir and the snapshot goes away. So no special tools, very easy to use, very powerful, not having to sort of predefine these things. The architecture then is sort of intended to make it so that you can build a system that actually scales and is sort of self-managing and self-healing and so forth. But there's then this sort of the next step of actually you as a storage administrator having to deploy it on actual hardware in an actual data center and actually keep it running. And that can be non-trivial a number of different ways. So how do you do that? So there are a number of things that we do and hope other projects do to sort of make this as painless as possible. So the first step, obviously, is installation. No, actually, the first step is to actually deploy and rack your gear, but I'm not going to talk about that because I'm a software person. Presumably, somebody has, trucked your machines in and racked them up and plugged them in. The first step after that is actually installing the software. So, we do the basic things. We work with the upstream distros to try to get things integrated into, Debian, Ubuntu, Fedora, OpenSUSE, all that good stuff. We also build all of our release packages for all these different distros so that you can always get the latest version. The distro stuff is always going to lag by several versions or half years or years. That can be problematic. So we want it to be as easy as sort of configuring your system to just go look at the upstream repo and do an apt-get and you get all the software and you're done. But it's not always that simple. So one of the sort of related problems with installation is that you have this deployment. You've got 1,000 servers and suddenly a new version comes out. It's not practical when you're running a highly available internet service to schedule a maintenance window, shut everything down, upgrade it, and then restart it again. So what we have to do is support the ability to do a rolling upgrade where you upgrade each server individually or a rack at a time or something without compromising availability and have sort of the system continuously working. So on the back end, we have to do all the hard work of making sure that all our data types are encoded in forward and backward compatible ways when they pass over the wire and so forth. So you can actually do this on a running system without shutting down. And then testing all those paths, it's a lot of good fun. On the flip side, there's also we build all the infrastructure to make sure that it's very easy to test new code. So we use tools that take every branch in our Git tree and actually build release packages for them. So any person can point to a random branch the developer pushes out and say, try this out, maybe it'll fix your problem. So you can push out hot fixes, you can do very easy testing, it just drives all our QA infrastructure. That makes it good times all around. Sort of the next step after installation is how do you actually configure the system? You've got thousands of nodes. How do I make that all work? The short answer is that you don't want to have to configure it. So Ceph will keep as much as sort of the internal cluster state managed internally in a very safe way, managed by Paxos in sort of fully consistent fashion so that it actually can give you the right answer when you ask it to do things. But there's always some stuff that you have to configure. So on individual nodes, you have to tell Ceph, which block devices am I supposed to consume to actually present storage to the cluster? What are the logging and tuning options, stuff like that. So there are a number of different ways you can do that. You can build a single configuration file that describes your entire cluster. If you're sort of in the old school, you can use a single system image root or SCP that to every host or something, and so it's sort of an easy management. On that side, if you're sort of in the new school of thought, more DevOpsy world, you can use things like Crowbar and Juju to automatically generate these configurations in a dynamic way, and they're sort of very minimal. So we want to sort of encapsulate all these different ways that people consume storage and hopefully point people in the direction that we think is going to be the easiest and most friction-free. So we want to be flexible. The next step then is, how do you provision these systems? And the key here is that you have to embrace the fact that your cluster is dynamic. You have nodes that you're deploying as you expand the cluster. Nodes are constantly going to be failing. In a large system, there's going to be sort of, at any point in time, there's always going to be something that's failing and recovering because of disks or hosts or network flapping or whatever. And so you have to sort of think of this as a first, as a design principle and so forth. So what Ceph tries to do is identify sort of the minimal amount of information about the system that it needs in order to sort of automatically bring itself up. So let's take a step back. Sort of the ideal vision is that you would, unload a truck and take a whole bunch of hardware, rack it up in a data center, turn it all on, and it'll sort of magically self-organize into this storage cluster that's all ready to go, right? That's sort of the vision. And so to support this, we need to sort of figure out what is the minimal amount of information that we need in order to make a cluster self-organize. And then what do we sort of leave to the tools to sort of handle. Ceph itself doesn't want to be a provisioning system, but we want to make sure that we operate well with the ones that are out there. So we identify the minimal amount of information we need to have a quorum for the monitors, and then everything else sort of is arbitrated and organized by those. So we build simple scriptical sequences and provide all the hooks so that the external tools can do the rest. So it's very easy for you to write a Ceph cookbook or a Juju charm or whatever the Puppet equivalent is to spin up a host, make sure it's configured, and have it join the cluster, and have that happen in a very painless and automated way. For some people, that's great. They're Ceph diehards, and that's what they want. For other people, you just want to stand something up quickly, and you want to just sort of see the system work. And so there's a new tool I want to talk just a little bit about called Ceph Deploy, whose goal is to make it very easy to sort of bring up new clusters in the system. And this tool is actually sort of a minimal wrapper that tries to use all the same hooks that all these automatic provisioning systems would do. So the basic idea here is that you would say, Ceph deploy new, I'm going to have a new cluster, these are going to be the monitors. That just sort of generates a unique ID and says this is what it's going to be. And then you run a command that says, go deploy a monitor over on that host, and it'll use SSH and your pre-configured keys, and it'll go start up the daemon, and it's all ready to go. You'll start up a couple other monitors, they'll form their initial quorum, and you'll have a Ceph cluster that's sort of in its infancy. And then you can run other commands to say, on host 2, I want to deploy an OSD using SDB as the data drive and SDI as the journal. Maybe I'll create another couple OSDs. Maybe I'll do ceph-w so I can watch it sort of do its initial peering, and that storage will come online. At this point, the system is totally usable. And I can run all this out of my, my home directory on my laptop if I want. And then, maybe some time goes by, I need some more storage, and so I can run it again, and I can create another OSD on another node. So the idea here is to make it very simple to bring up new clusters and to take existing ones and expand them. In sort of the large-scale deployment world, that isn't actually a very useful approach. What you kind of imagine, if your business guys are doing their job, is that you'd actually have an entire data center that's just filled chock full with hard drives and machines. And hopefully once a week you'll go through and you'll find all the disks that have failed, and you'll pull them out and replace new ones, and maybe every once in a while you'll plug in a new rack and it'll magically come up and join your clusters, right? So that's sort of what the goal is. So the question is, how do you get sort of this turnkey solution that you would get out of an enterprise array where the light blinks and you swap it out and put another in, and then put another drive in, and it sort of magically works? How do you get that sort of complete solution using open source software and all these tools that are going to be loosely integrated with all these different frameworks? And so what we're building is something that is actually pretty cool. So the basic idea is that you'd have a bunch of disks. You would essentially mark them using a GPT partition type label as this is a blank Ceph disk, and it's it's available for Ceph to consume if it sees it. And so you mark a bunch of disks, maybe you have a big pile of spares or something like that, then you put them on your cart and you start walking through the data center. At that point, you just plug it into a server. UDEV will generate an event that says there's a new disk, and then either a UDEV rule or maybe an upstart rule, something like that, will say, oh, this disk is marked as free for Ceph consumption. And so it'll call this hook called Ceph disk activate on the device node. Yeah.
Just with your piece there about GPT, you say fix your UID?
Yeah.
I mean, the UID of the disk doesn't change, or you have a fixed UID for Ceph?
The GPT lets you do a type on the partition,
Yep.
so you mark the type as a UID that we just said, this is the Ceph type. So you just mark the disk as this is free for Ceph. We don't want to just take any random disk that you plug in and start formatting it and plugging it into the system, so we need some way to sort of
Yeah, just
control
which bit within GPT you were using, that was it.
I'm pretty sure it's the type, yeah. I didn't actually write that part. But basically, you just sort of call this hook. It will, mount the disk, it'll format it, it'll give it assign it an OSD ID, it'll remount it in the right location. Optionally, if you have it configured properly, it'll actually adjust the cluster configuration that says this OSD is now, in this rack in this host, so the system sort of understands the topology of the infrastructure. And then whatever your init system, whether it's sysvinit or upstart or whatever, it'll kick off the job that'll actually start up the daemon. The daemon starts up and does its usual thing where it registers with the monitor and says, I'm now up, this is my IP address, I'm part of the cluster, and start chatting with its peers. The key thing here being that there's sort of no manual node configuration. So in your ideal deployment, you rack the server, you plug it in, maybe you kick off your Ceph thing that auto-configures the host. Maybe it just knows that it's in this rack. And then you plug in the disks, and then all the Ceph rules kick in, and they magically instantiate these OSDs and join them in the cluster. And you don't have to sort of do any manual, tedious configuration. So that's coming very soon now. Very interested in hearing feedback for people who actually tried to manage these sorts of things and what you think of it. So just a very quick status update on sort of the Ceph project, where we're at. Ceph is this distributed object layer. It has all these different ways you can access it. If you're looking at the low-level APIs or the object gateway or the block device, then it's great. People are running it in production for deploying their clouds. It's pretty awesome. If you're looking at the file system, it's a whole new level of complexity on top of that. It's not quite ready for production. It's definitely not ready for production, so don't run it just yet, but we're getting there. That's sort of the long-term goal, is to have this unified system where you can run sort of a single storage infrastructure. You can consume it in lots of different ways, not have to manage a point solution for this type of storage and a point solution for that type of storage. The things that sort of eats all your time and attention as a storage administrator. So very briefly, just why we work on Ceph, why we think it's important. There are limited options for open source storage, particularly when you're talking about scale, when you're talking about deploying cloud infrastructure. When you start talking about enterprise features like snapshots and so forth, then you can't get those at scale from very many places. There are lots of proprietary solutions, but they tend to be very expensive. They tend not to scale very well at all in many cases. They definitely don't scale out, certainly not when you start talking about price. And they also tend to marry a hardware and a software solution, which means you're stuck buying their box. It's expensive and you don't have the flexibility. So all these things make users hungry for open source alternatives that give them control, they give them the scalability, the sort of cost effectiveness, the features that they need, and sort of an open interoperable format. So that's what I prepared. Any questions? Yeah.
The first one is, thank you very much for the talk, by the way. The first one is the objects themselves.
Mm-hmm.
Do they have a fixed size, or are they?
They can be any size. So an object can be a couple bytes. It could be several gigabytes. Objects also can store not just bytes. They can also have attributes on them, and you can store keys and values in them. So you can think of it like a Berkeley DB file with efficient key range queries. So objects can do all kinds of crazy things.
So when you do storage from the REST style API, you can throw like ACL attributes or whatever onto it.
Right. So there's that's the low level objects that Ceph is providing with Rados. The RESTful objects are actually built on top of that.
Oh, okay.
So a RESTful object might be a terabyte image file that's actually striped over Rados objects, and the ACLs are stored in attributes on those objects, and there's an index object that keeps track of everything in your bucket, and so it's using all sort of the bells and whistles of the underlying object store to prevent this sort of higher level abstraction.
And the same sort of stuff with the file system, where you got like little metadata bits and heap pieces here.
Right. So the file system has metadata servers that manage the hierarchy, but they're actually storing all that directory metadata in objects in the object store, and they're using key value objects for file names and on each directory and stuff like that.
If I can ask just slightly.
Yeah.
The Ceph file system adapters, be it like kernel level or fuse or whatever like that, do any of them do failover at the moment, so that they'll talk to any member?
Do they do what?
So they'll talk to any member of the cluster rather than they will do?
Yeah, so the key idea with this sort of scale-out infrastructure is that you want the clients to be able to talk directly to the servers. You don't want to have any sort of proxies or gateways. And so using this hashed algorithm means that a client can calculate which server to talk to and talk directly to that server. So in the file systems, files are striped over lots of objects. Those objects are randomly distributed. The only place where that's not true is with the Rados gateway, because you're speaking a legacy protocol, HTTP, and it has to go through an endpoint and then get branched out. But you can build lots of gateways and scale them out that way.
So when will the CephFS be as awesome as everything else? Any idea of that?
That is the question. So we're hoping that for the next sort of major release, Cuttlefish, which will be late spring, something like that, that will have a more stable file system solution that we can have people actually run without risking or as much fear of losing their data. Having the sort of full-blown feature set where you have, lots of metadata servers and using all the snapshots and so forth that are all very complicated is going to be further out. So we're continuing to invest in that, but there's a lot of time. Right now we're working on building some of the underlying infrastructure to support robust NFS exports and FS-check, so we can look up things via inode. Having things like FS-check are important probably for people who are storing real data in the system. So for the file system in particular, that's important with all the.
And just one more really brief one. Very early slide you said tens to tens of thousands of machines. What about below 10?
You can run it on one, and you just won't replicate. So I regularly run it on my laptop. Yeah,
so around 4 it actually makes.
Yeah. If you're running 2, there isn't like a huge value add. All the complexity of Ceph with data distribution and so forth doesn't buy you a whole lot. You might just want to do a RAID mirror or something on one host. So it's usually 3 or 4 hosts when you actually this starts making sense.
Are clients aware of the I/O usage of just say one node? For instance, if you've got the one storage node which is being absolutely smashed, are the clients aware to be able to go to the secondary? And also, can you do essentially I/O QoS where you can guarantee for a particular object at least a minimum IOPS?
QoS is hard. So generally speaking, no, not yet. The challenge with detecting those hotspots and dealing with them is having some place that the traffic is passing through, so you can actually observe that and redirect the traffic. So the basic principle with Rados is that the client goes directly to the storage server. And so if you have 1 million people suddenly decide to talk to the same person, there's nothing you can do to sort of prevent that. Yeah, so if you know ahead of time that it's hot, then you can distribute it across replicas, but you don't always know. So in the file system, we'll be building things so that if lots of people are opening the same file, it'll make them read from multiple replicas of the file data, for example. But if you're using the raw object store, then you just don't have that control because you're giving them sort of direct access. So it's usually a layer in front of it that you sort of build those sorts of things in. The file system has all kinds of things to try to control traffic on the metadata level. So one of the original use cases is these HPC clusters where you have 1 million cores suddenly open a file in the same directory. And so there's a lot of sort of trickery to sort of proactively distribute that type of workload if the cluster thinks that directory might get hot. But that's at the file system level. At the raw object level, you don't have that.
Sage, just wondering, how do you actually get compute to run where the storage is located, for example? Thinking of it like Hadoop with HDFS.
There you are. Sorry, you'd repeat.
How could you get something like Ceph to be as flexible as, say, HDFS, where you could get the compute to run where the storage is located, like, for example, where the objects are? I mean, is such a model possible?
Yeah, I mean, you can do exactly what Hadoop does with HDFS, with Ceph today, actually. There's a prototype plugin that links into Hadoop that exposes the same functionality that HDFS does using Ceph to Hadoop. So the only real trick there is that Hadoop asks HDFS where the data blocks are stored, and then it schedules the job to run on the same node. You can do the exact same thing with Ceph.
One of the great things about open source is people using your software in exactly the opposite fashion you wanted them to. So my use case is we've got plenty of nodes, but they're spread transcontinentally. How hard-coded is the assumption that the cluster can talk to itself with really low latency? And what would happen if I was to have one of those be my laptop and another one be a server in California and?
So it's not so much hard-coded as it's sort of implicit assumed in the design. So the main consideration is that replication is synchronous. So when you do a write, the client doesn't get the acknowledgement until all replicas have been written, because the assumption is that you care that your data is actually written, and we want to have strong consistency. So you're just going to have a really high latency on writes if you're sending it over a transcontinental link. The only other issue is that by default, the tuning for all the heart beating stuff that's going back and forth to detect liveness might cause problems if you have flaky links, so you have to increase all those timeouts. So it's not, having sort of a robust multi-data center solution is something that's on the roadmap, but it's not there yet.
Right, this is kind of a two-part question. The first bit is about the crush algorithm. Is that used for CephFS and the RBD layer and for all the different access points apart from, of course, HTTP?
So it's sort of intrinsic to Rados itself. So all of these services are built on top of Rados, and so they all
That's ridiculous.
All right.
That should be on silence.
They knew that you had the mic.
Yeah. Yeah, wish it would. The other piece was, in terms of being able to handle that, the failover scenario, that some of the nodes the algorithm would be talking to have now failed, your data's being re-replicated. At what point does your client realize, is it when it first tries to access that data?
Usually before that, but in the worst case, it'll find out when it tries to access it.
How does it know earlier?
So normally the client is doing lots of random IOs to various nodes, and every time it sends a message, it's saying, by the way, I have version 112 of the cluster state map. And if a server ever says, oh, well, I have 115, it'll just say, by the way, here's the diff. These 3 nodes have gone down since then. And so usually the client will find out about these changes before it actually talks to the one node that went down. But in the worst case, it only has 1 IO in flight, it's talking to the one node that's down. It'll wait a little bit. If it doesn't get a response, it'll ask the monitors and say, is that guy still alive? Yeah.
Sage, in the previous talk, John was mentioning some of the challenges of creating a block device on top of an object store. Could you please elaborate on how Ceph does that?
Yeah, so in principle, you're storing all these objects, and you want to have a virtual disk. You can just take that disk and you can break it up into pieces and store each of those pieces in an object, right? So that's the high-level view. John's point was that Swift is aiming for availability, not consistency. So everything that you normally build on top of the block device assumes that if you write something to disk, you're always going to get the right answer back, or else you're going to get file system corruption and have to run FS check. Ceph takes sort of the opposite approach, where we're aiming for strong consistency, and we'll give you no answer instead of the wrong answer. And so it's better suited for example, building a virtual disk. So all we basically do is we say you have a terabyte disk, we'll break it into 4 meg chunks. Each of those 4 megs is stored in an object. And that object is randomly distributed across the cluster. While we're waiting, I wanted to mention that there's going to be a tutorial tomorrow that Florian's doing at 1:20 in CC6. So if you want to actually get sort of your hands dirty and a closer look at how this works, you should definitely come by.
How big is this cluster state map that you're sending back to the client?
It's usually 100K, 10K. All it's doing is it's listing the names of the nodes and their IP addresses, and it has sort of a tree structure that says how they're organized.
How often does this get sent?
It's updated whenever there's a change in the cluster state. So if a node goes down, then the new version's published. If it comes back up, a new version's published. And it's distributed as a diff. So if you have 110, version 110, you'll get the diff to 111, and that's sort of gossiped around the cluster. So it tends to be very lightweight.
Given the distributed nature of the underlying blocks of data, and I know this isn't ideally what the question you want from the end user, what's the approach then to backing up that data?
That's a difficult question. So people who are building these, multi-petabyte systems, the goal is to not have to back it up, right? You build a system that has sort of the internal redundancy so that you don't have to slurp all that data off to a tape array or something, annoying like that. For early days, for some snapshots, yeah, right. But the sort of the flip side of that is that for any new piece of software, for any distributed system, we talk a lot about single points of failure. The software is the single point of failure. So in early days on any system, you want to have some redundancy until you sort of have some faith that that system's not going to lose your data. So if you have a small subcluster and you care about the data, maybe you should back it up. The goal is to get to a point where you don't have to do that.
Hi. So when are we going to be able to change the number of PGs and pools?
Actually, you can do it now. We just haven't told everyone about it. Yeah.
Can you increase or
you can increase? You can't decrease yet.
You can't decrease. Okay.
Yeah. So aim low, I guess. Yeah. Yep.
Sage, I was wondering, how do big Ceph deployments handle day-to-day operations like mapping failed drives, failed OSDs to physical drives? Like, how do they run big clusters with the assumption that disks will fail. How do they handle that?
So there's a command called Ceph health that'll give you sort of a summary of Ceph's internal view of the health of the system. It'll say these 10 drives are dead. Ceph identifies things by the OSDs by number, and it'll give you an IP address. So you, as sort of the external management framework, has to be able to map that back to a particular node. So in DreamHost's case, they use Chef, and they have some weird nice command that'll spit out which machine it's in. Or actually, no, I think they put the node number in the IPv6 address. So they can just look at the IP address and they'll know which node it's in, and then they ask their system where it is.
Okay, and the other question, is it common to deploy Ceph in multi-site setup, provided that the latency is not a problem?
Nope, and there are people doing that today. So if you live in a small European country, even a large European country, for example, you can have lots of data centers spread around that actually have low links. If you happen to be a telco, it's great because you have sort of infinite free bandwidth. And so there are people that have dedicated 10 gig links, multiple data centers, and they're using RBD volumes distributed across data centers and doing live migration, and they get high throughput, and it still works. It's pretty cool.
Thank you.
Sage, how does Ceph handle end-to-end data integrity?
In a fragmented way currently. We do additional checksums on everything that goes over the network because TCP checksums aren't good enough. When you're storing in Btrfs has all its checksums. We aren't sort of bridging the gap and making sure that the checksum goes all the way through to the file system and verifying it on the way back. That's sort of future work. There are these sort of emerging diptychs stuff that lets you API so that from user space you can say this is my data and this is the checksum, and the idea is that it'll pass all the way down through the storage system, all the way through the controller to the disk and get verified all the way back up. That's sort of the end goal, but there's a lot of work, a lot of gaps to fill to get there.
So it sounds like Ceph handles failing nodes and failing disks really well. In my experience, that's kind of not the big problem. The big problem is things that are going really slow or kind of half broken. Does Ceph have a bunch of infrastructure to help you handle that sort of situation?
There are all the tools to sort of respond to it, but it doesn't magically detect that situation for you. So we expose all these metrics and all the storage daemons, and their integration glue to collect, aggregate all these statistics and dump it in Graphite, for example, but there's nothing that monitors that and says this OSD is running half as fast as it's supposed to and tells the cluster to not use it. But the hooks to actually make the cluster respond to it are sort of there, but there's not a closed loop just yet.